integrate 10x minus 23 over 2x minus 1, x minus 5. So it's one polynomial divided by another polynomial. And someone was nice and came along and factored this for us, factored the denominator. So that's great. But because we've got a rational function, we are going to have to start off by working out a partial fractions decomposition. And this is why we mentioned that the denominator is already factored, because if it wasn't, that would be the first thing we do. Okay, so with two distinct linear terms, this is our setup here. What do? Well, we need to find a and b that make this work. We will be able to find these constants. Okay, so what are we going to do? Well, I don't usually show it, but the first thing I do is I multiply both sides by this denominator. Okay. I don't usually show it just because it takes a little while to write out, and it's something that I'm very used to. But you might not be, so we're going to write it out. So just multiply both sides by that denominator. It's really nice when you do it if it's factored, because then you can very clearly see the x minus 5s canceling out, the 2x minus 1s canceling out. So we're left with 10x minus 23 is a times x minus 5, and b times 2x minus 1. Okay. Now, what could we do here? Well, there's a couple approaches. One thing we can do is try to find values that are roots of these factors of a and b. So 5 and 1/2 would work nicely. Okay. And then plug those values in, because this expression should be equal to this expression regardless of what x is. Okay. And that can help us find a and b. That's not the only way to do it, of course. You could sort of expand this out and get a plus 2b times x plus, minus 5a plus b. Okay, we expand and rearrange and simplify things. And the way polynomials work is two polynomials are equal only if their coefficients are equal. So you would say, aha, that means 10 must be a plus 2b, and 23 must be 5a plus b. Okay? So that's another approach. I'm not going to do that one. Sometimes I do, but I find the plugging in roots is just a lot faster and a lot cleaner. Okay, so that's what we're going to do. So first, we're going to let x be equal to 5. So 10 times x is 50, minus 23 is 27. A times 5 minus 5, that's going to be 0, so we won't care about that. And then b, 2 times 5 is 10, minus 1 is 9. So 27 is 9b. From there, we can work out b must be 3. Okay, now we need a. And if we want to get rid of b, we want to multiply it by 0, we can plug in a root of 2x minus 1, like 1/2. Okay, so 10 times 1/2 is going to be 5, minus 23 is negative 18. Then we will have a 1/2 minus 5. We'll work that out in a second. And then b, 2 times 1/2 minus 1. Well, that's just going to be 1 minus 1, 0. We can ignore it. So negative 18, 1/2 minus 5. Maybe we could rewrite the 5 as 10/2. 1/2 minus 10/2 is negative 9/2. Okay. Multiply both sides by 2. Negative 36 is negative 9a. Get rid of the minus signs on both sides. Divide by 9. We see that a is 4. So, after all that work, we have managed to create our partial fractions decomposition. So 4 over 2x minus 1, and plus 3 over x minus 5. Great, there's our partial fractions decomposition, except that wasn't what we're asked for, that's just a stepping stone on our way to integration, because now we can rewrite the integrand, the thing that we're trying to integrate, as a over 2x minus 1 plus b over x minus 5. And these are simpler things to integrate. Okay. Now, the derivative of x minus 5 is 1, so we can take advantage of this nice little trick anytime we're trying to integrate derivative of a function over a function. Okay. We just get ln of that function. So that means we're going to get 3 ln absolute value x minus 5. Okay. But be warned. Okay. I see partial fractions. I teach so many people partial fractions over the years, and sometimes people will rush and they'll say, "Oh, I got to this part. Okay, I did the partial fractions. That was the part that was for marks. That was the part that was hard." These are the things they say to themselves. And, "Oh, this is easy. You bring out the factors, and then whatever's on the bottom just goes in your ln." So 3 ln x minus 5. You see so many of these. Tons of textbooks over the years. They have these, and people just make this connection. That goes inside the ln. And so somebody's just going to rush, and they'll just say, "Okay, the 2x minus 1 goes in the ln." Except that's not the case. Okay? I find this is actually something that modern textbooks lack a little bit, is situations where you don't have a leading coefficient of 1 in a linear term, because this simply isn't how it works. Okay? It works over here because the derivative of x minus 5 is 1, but the derivative of 2x minus 1 is 2. We don't have a 2 up on top, so we can't use this quick trick. Okay? So you have to be aware of that. Otherwise, you will get caught by this rushing trick, this dream that that's the connection that we need to make. No, no, no. Okay? So what could we actually do? Well, there's lots of ways to do it. There's a nice sort of building block that you can actually memorize. It says anytime you got 1 over ax plus b, it's 1 over a ln absolute value of ax plus b. That's fine. That's a good thing to remember. So in this situation, you'd have 1 and then negative 5. So 1 over 1 ln x minus 5. You'd get what you've got. But that would help you here, because you'd remember you need to do 1 over 2, because your leading coefficient is 2. So that's one thing to do. Okay. Remember that little building block there and how it can help us. Another thing to do is say, well, I need to be careful. I need to make sure that the derivative of the bottom is the thing I find on top. The derivative of 2x minus 1 is 2, so maybe I shouldn't have been so hasty when I pulled out this 4. Let's only pull out 2 of that and leave a 2 on top. Because now the derivative is on top. Now the derivative of 2x minus 1 is on top, and we can apply this little shortcut. Okay? So a lot of people forget that. So it's something to be on the lookout for. And there we go. All together, there's our final answer.